Alright, so I just want to introduce you to the weak acid strong base titration notes. If you would just copy these down, then we'll work through the calculations in class tomorrow. But when you have a weak acid and strong base titration, or if you have a weak base and a strong acid titration, what you want to do in order to be able to find the hydrogen ion concentration after the strong base is titrated, you want to, first of all, do a stoichiometry problem, where you're going to assume that the hydroxide from the strong base and the weak acid are going to react 100%. This is just like what we did with the buffer calculations when you added a strong base to a buffer. Remember the OH got attacked by the weak acid in the buffer? This is the very same kind of calculation. You're going to react at 100%. Then you'll be able to determine the amount of the amount of weak acid and the conjugate base that will form. And at that point, it's an equilibrium problem. What you can do is you can then use the Henderson-Hasselbalch equation. So we'll be following these steps in order to proceed with our titration calculations if we have a weak and a strong combination. So I want to at least get us set up so that tomorrow we can proceed with the calculation itself. So let me just remind you how this is similar to what we did on the strong acid, strong base titration that we did in class today. Here we are considering the titration between 50 milliliters of 0.1 molar acetic acid. Now notice this is a weak acid, and that's what's in the flask. And you're titrating with 0.10 molar sodium hydroxide. So in the burette here, we have our sodium hydroxide, and it is 0.10 molar. So just like before, we're going to figure out how many millimoles of our acid are in the flask. And to do that, you take the volume times the molarity. So again, we're going to say 50 times 0.1. So 50 times 0.1 is going to give us that we have 5.0 millimoles of the HC2H3O2. And of course, our millimoles of our base are going to fluctuate because we're going to be adding that into this acid. So our volume is going to be changing. Now, just like in the previous example we did, we're going to figure out the pH in the flask before we add any sodium hydroxide. So keep in mind, before we start our titration, the only thing in this beaker is the weak acid, which is the acetic acid. The acetic acid here, remember they told us it was 0.10 molar. And there were 50 milliliters in here. So this part of the calculation is before you add any of your titrant into the flask. So we only have a weak acid solution here. So this will be carried out like we did in chapter 16. So HC2H3O2, this is a typical equilibrium problem. You pull it apart, H plus C2H3O2 minus. This is your equation. You're going to ice your problem. You're going to fill in your amount. So here we have 0.10 molar, 0, 0. Now remember, since this is just a weak acid, it's going to dissociate less than 5%. So minus X plus X plus X. We can neglect the X here. So we can assume an equilibrium. 0.10 molar is going to be the acetic acid concentration. X and X is going to be the hydrogen ion concentration. So when you set up your law of mass action, the Ka is equal to hydrogen ion concentration times the acetate ion concentration divided by acetic acid concentration. So we're going to plug in our values here. We were told in the previous part of the notes that the Ka was 1.8 times 10 to the negative 5th. So that's going to be equal to x squared over 0.10 And when you cross multiply and then take the square root, you get your x equal to 1.3 times 10 to the negative 3 molar. Now remember, in this case, x represents our hydrogen ion. So that means if we take the negative log of that, pH is equal to negative log of 1.3 times 10 to the negative 3. So the pH is equal to 2.87. So this is the pH of the acid in the flask at the beginning of the titration. So we'll pick up tomorrow with the calculation as we add the strong base to the weak acid.